Hello everyone, welcome to today's ARCHER2 webinar. Today we have Ralph Burton from the University of Leeds, who is talking about modelling volcanic plumes using ARCHER2. There will be time at the end of the talk for questions, but if you want to ask anything during the talk, feel free to write your question in the chat box or raise your hand. So yeah, without further ado, I'll hand over to Ralph to start the talk.
Great, thank you. Well, thanks for the introduction. Yep. This is some work that a few of us in CAS and elsewhere have been doing over the last few years, and it's sort of basically a response to the question of trying to model volcanic plumes. So the work that I'll be showing today probably covers for about the last sort of 6 or 7 years of work. So it's still ongoing now. So some of the collaborators, and the usual disclaimer that there are lots of other people involved, and my apologies to those if they feel they should be mentioned. So moving on quickly then, just do a very brief introduction to what we mean by an atmospheric plume. So they can vary from very small scale plumes, such as you might get in a laboratory study or something of that nature. So that might be something very, very small, and then going up in size to the sort of plumes that you see coming from power plants. And there's a very sort of a very bad, if you like, example of that in Poland. And they can also be created on purpose. So you've got a picture of a smoke screen here in Vietnam. And lastly, the one I'll be focusing on more today is the sort of volcanic plume. So that's quite, this impressive picture here is from Mount Etna in 2015. So they've got a lot of things in common, plumes of this nature. As you can see, they do. You could draw, if you had a pen, you could draw an outline of each plume, and you'd be fairly sure to be able to get a sort of fairly simple mathematical representation of that plume. So there are some sort of basic plume properties that come in handy for modelling purposes. But to do this in a more complicated situation, for example, over a country with complicated geography, or where there's lots of turbulence, or where the atmosphere may be stratified. So stratification here refers to the way that the temperature changes with height. You may also have things like particles, ash particles, for example, or gas itself may be settling due to its inherent density. And also weather patterns might move the sort of pollutant round in lots of complicated ways. So to do this properly, it does require a full numerical model. And this is an example here of somebody has produced a simulation for last year for the eruption from La Palma. And so this is a plot of SO2. As you can see, it's transported a long way across all of North Africa into Europe and beyond. So it's that you wouldn't be able to do that without a full numerical model. It's quite a complicated and challenging task. So the model that I'll be talking about today is the Weather Research and Forecasting, or sometimes abbreviated to WRF model. It's a state-of-the-art model, state-of-the-art forecasting model. It's got over 40,000 users in most countries in the world. So the X's are generally in Africa and the Middle East. And it's also been used operationally around the world as well. So it's a weather prediction model that is used operationally. So one of the sort of reasons why it's so widely used and adopted is because it's free. There are no licensing restrictions. You can change it how you wish. There are no restrictions on that. And almost as importantly, the data to initialize the model. In any model such as this, you need if you like, a guess at the state of the atmosphere in order to drive the model forward. And that's also free as well because of the sort of American Freedom of Information Act. So because of those reasons, and because it's generally thought of as being a good model and can be used at scales from hundreds and tens of kilometers down to sort of hundreds of meters, it's a very popular model. and it's got very sophisticated representations of various atmospheric processes such as turbulence, microphysics, radiation, land surface properties, and all that kind of thing that go into a very sort of sophisticated numerical weather prediction model. So it's actually an American model developed in America, as I say, primarily at NCAR. It's still being developed, so about every 6 months to a year there's a new version or a new release. Documentation is excellent, as is the support from NCAR. They have a sort of like a dedicated support desk that answers questions from users. There are numerous sort of community efforts, forums for that, and NCAR also hosts courses, as do NCAS, I should say, online at present. So it's got a lot going for it. And it's quite easy to get to run as well. So the very sort of basic thing, all you need, as long as the usual things you get in a sort of Unix distribution, are netcdf libraries. You can, if you're depending on what you need to do, you may need to add certain other libraries, but they're not strictly speaking necessary. So the code base uncompiled is about something of the order of 100 megabytes. But the main sort of space taken up by the model is the static data set, and that consists of a worldwide representation of topography, land use, vegetation types, soil temperature, all these kind of things. So all these sort of static data is needed to run the model. And on a model, on a machine like Archer, it takes about an hour to compile. And there's lots of installation scripts that are supplied. Here's an example of running the configure script on Archer. So what you just sort of set the configure script running, and it comes up with a whole bunch of various options for you to use, how the parallel processing is handled, which compiler you wish to use, all this sort of thing. So the one I've used is circled here. Excuse me. I don't have much experience of using other compilers, but I believe you can get significant differences depending on which compiler you use. But the one that I've highlighted here has been easily sufficient for our tasks. So here we just select number 34, and all being well, everything compiles. It's very well structured for a sort of an atmospheric scientist, because the bits of the code that an atmospheric scientist might wish to change are all written in Fortran, and lots of atmospheric codes are still written in Fortran. All the sort of really hard bits of the software, the bits that deal with the parallelization, the input and the output, they're written in a mixture of Fortran and C, but they're sort of kept separate from the bits that most atmospheric scientists would want to change. So from a scientist point of view, it's very well structured, the model, because it's very clear how to change things, and the bits that you can do damage to, if you like, are kept separate from you. And just a quick note about the scaling. So it scales up to many thousands of processors. So it scales well here, up to sort of over 30,000 processors. The initialization time is more, excuse me, so reading in the meteorological data and so on, that's fairly constant, because that's mainly a serial process. So these are for a standard WRF benchmark test case. The number of cores that we've used is generally about of the order of several thousand or lower. And the model runs by decomposing your domain into a subset, and assigning each part of the domain an MPI task. So I'm afraid I'm not really a big expert on the sort of parallel processing side of things. And one of the beauties of the model is that you don't really need to sort of deal with all that side of the model. As I say, it's all sort of compartmentalized, so that this kind of thing is kept separate from you, if you like. So in order to take this standard numerical weather prediction model and simulate the volcanic plume or a dense gas, which I'll be talking about as well. So what you need to do is you can either add a thermal perturbation at the surface, so that something representing a hot surface, if you like, something that's equivalent to, well, not equivalent to, but analogous to a volcanic source, and then add a tracer co-located with that. That's a very brief way to simulate a volcano. So in other words, in this approach, it's very like an extreme thunderstorm, if you like. It follows the same patterns as a very, very extreme thunderstorm, where you've got heating at the surface, air rising, then spreading out as it reaches its level of neutral buoyancy, as it's called, so to give the typical volcano shape, and I'll show an example of that in a second. And another application of this, which is just as important, is to model dense volcanic gases. So whenever there's a volcanic eruption, it's often accompanied by release of potentially dangerous gases, and it's also important to track where these gases are going as well. People primarily near to the eruption on the ground. And just a technical note here, when you do try to run it in a volcano mode, for the time step, in other words, the time in between different model steps needs to be set very low, because you get very strong updrafts, and as a consequence of the CFL condition, you need to take very small time steps. But that's just a technical, excuse me, a technical remark on the volcano model. That doesn't apply to the dense gas model. So this is an example of a simulation of a volcanic plume using WRF. As I say, it's initialized with a very strong surface heating, and as you can see here, it rises up, overshoots a certain level, and then spreads out at that level, and that level is its neutral buoyancy level. So it's spreading horizontally at that point, and this gives you a good representation of a sort of basic volcanic plume structure. And here there's no wind. If there was a wind, obviously the plume structure would be bent over, as it's called. But we can test various properties of this simulation against various theoretical properties of volcanic plumes that I mentioned earlier. The sort of some of the essential qualities of plumes, and it does perform very well. This was done on the old Archer machine, in actual fact, using, I think, about 1,000 processors. So this would have been 150 by 300 grid points. So it's not a particularly big simulation, but because of the slow time step, it does require a large number of processors. Here's an example of simulating a dense gas. So this is some other work we've done. In this case here, you've got the WRF model releasing a pool of carbon dioxide in the middle of the domain. So this is representing the geography around Lake Nyos in Cameroon. And in 1986, there was a sort of what's called a limnic eruption. Excuse me. So a large lake in Cameroon overturned, in effect, and lots of carbon dioxide was released instantaneously without any warning. And the carbon dioxide spread into the sort of surrounding valleys, and unfortunately killed over 1,700 people, and I think thousands of livestock, and injured many more. It also sort of led to a widespread destruction of crops, because the dense gas moved so quickly that it with such a force that it could actually destroy crops. And so here you see the modelling of a dense gas. This was on the old Archer machine as well. And as you can see, the dense gas kind of settles in these sort of valleys and moves down almost like a liquid. So unfortunately, there's no real way to test how accurate this is in this particular instance, but we have tested it against various sort of benchmarks and other tests for sort of gravity currents and so on, and it does a good job. So moving on to a real application from more recent times, in one of the NCAS research flights, that were flying around Iceland. It was noticed by chance at first, but there were very, very large spikes in measurements of carbon dioxide over the Katla Glacier, which is shown here. So the Katla Glacier consists of a number of potential sources, and the top right-hand plot there has just highlighted some of the potential sources of CO2. These are underground sources that are often associated with small stream outlets and so on. And these carbon dioxide measurements were so high, surprisingly high, then that's quite a few NCAS research flights went back there to try and quantify the amount of CO2 coming out of this first unknown source. We knew the source or sources, there may be more than one, was on the glacier somewhere, but it wasn't quite clear where. So the research flights did probably half a dozen flights in order to try and locate the source and quantify the amount of CO2 coming out. So we had initially we had 30 candidate sources, and so for each particular source, and one is shown here on the bottom left simulation, for each source you would simulate the release of carbon dioxide from this source, compare it with the observations, and determine if it matches the observations. If it doesn't, you could eliminate that as a potential source. So we did this 30 times in order to identify the source regions, and by a process of like using a sort of simplified Venn diagram. So I've showed in the bottom right hand panel there are sort of three such cases there. So this is comparing with 3 flights, and we could narrow it down to get a better idea of where the source is. So this took quite a lot of work to do this, and this would not have been possible without a machine like Archer. It was unthinkable, really. So each one of these runs, I think, used probably 512 processors for maybe 18 hours. So each particular run used quite a heavy sort of burden of computing. And this is the published results from that work. So the top left-hand plot are the actual aircraft measurements, where there's a where there's a sort of a red or an orange, a warm colour with high levels of CO2, and on the right-hand panel are the WRF measurements interpolated onto the flight track. So I think it probably did quite a good job, really. We were very pleased with the way it simulated the observations, and using some other methods, the WRF together with a sort of mass flux approach, we could confirm that this source, which is unknown still, was one of the biggest sources of volcanic CO2 on the planet, and nobody knew it was there. It's that we've not been back, because when we did these results, it was just before the first lockdown in effect, and we never got a chance to go back. But it turns out at the time it was emitting about 20 kilotons of CO2 per day. So it is a globally significant source of CO2, and obviously it's colourless, and nobody knew it was there really in such a remote location. But we will go back there one day to see if it's still happening. And an application from last year was there was an eruption on the Reykjanes Peninsula in March 2021, and here's a nice picture there of the vents. And so in this sort of volcanic system, there were when it was at its maximum, there were 5 vents in activity. This is on the southwestern peninsula, the Reykjanes Peninsula in Iceland, and was very active for several months. And you can see the clouds of various sort of gases being erupted simultaneously alongside the lava. And here's a couple more pictures. So what the Icelandic Met Office can do, they've got various very sophisticated calibrated cameras So on the top right-hand panel there is one of the Icelandic Met Office's cameras that can detect how high the plume is. So they've got these very highly calibrated systems where you can just move a cursor over where you think the plume is, and it tells you how high it is. And that's a key factor in initializing a model such as this. So we would then get from the Icelandic Met Office some information about how high the plume is, and that's a really crucial piece of information. And just another picture there on the left-hand panel there, just to give you an idea of the scale. The top circle shows a helicopter, and the bottom circle shows a group of tourists. So it became quite the tourist attraction in its early phases. So what happens when this initially occurs? The Icelandic Met Office issue what's called a VONA, or a Volcano Observatory Notice for Aviation. So you would get one of these appearing in your email inbox, and it really tells you that there's, when these appear, you know that there's something happening in Iceland. I should perhaps at this point stress that the primary responsibility for responding to such events lies with the Icelandic Met Office, the London Volcano Ash Advisory Centre, and the UK Met Office. So they're the people that have to take the big decisions about closing down airspace and so on. Excuse me. But NCAS has a memorandum of understanding, an MOU with the above institutions, and also with BGS, British Geological Survey. So we all sort of pool information and can supply simulations if required. So this is the kind of way that this information arrives. So you get one of these, and it, excuse me, it tells you whereabouts the volcano is erupting, what the current aviation colour is. So this was orange. So that means orange means there's an eruption occurring, and it's releasing gases, but it's not actually a danger to aviation at the moment. So if that said red, then that would be a major volcanic eruption, and the current aviation colour code would be red. So that could be a potential danger to aviation. So the VONA, this notice as well, contains information that allows people to start simulating the dispersion of gases and so on. So critically here, it gives an SO flux estimate of 19 kilograms per second, and it gives you the plume height to be 1 kilometer above sea level. So those are the crucial bits of information, and that's as well, together with the location of the occurrence, then that's in this sense a good starting point to run a simulation. So in this case, we agreed with ARCHER, very kindly allowed NCAS what's called like an emergency volcano allocation. So we were allowed to use this allocation exclusively, 256 processes on ARCHER2. So we were very, very grateful to the folks at ARCHER2 for allowing us to do this. So this then allowed us to sort of do this in real time operationally, if you like, rather than having to submit jobs to the queue and so on. So this was really great for us. And as I say, the inputs needed the release rate in kilograms per second, obviously where it's being released from, and the source depth. They're all crucial pieces of information, and they come from the VONA, the email from Iceland. Excuse me. So when this happens, and as look what happened, I think this started on Saturday. So that's as all these things always do. They started the weekend, but first thing in the morning. So what you've got to do first of all is adjust the source parameters in the model and then recompile it. And that takes about 15 minutes, and you just need to do that once. So the sort of configure scripts only recompile the parts of the code that you've changed. As I said, it takes about an hour to do the whole thing. If you just recompile the parts that are required here, it takes about a quarter of an hour. To pre-process the meteorological data, about 5 minutes, and using 256 processes, we could get about a 12 times speed up. In other words, a 1 hour wall clock time would give us a 12-hour forecast. And that's sufficient for these purposes in order to determine where the sulfur dioxide is going in this case. And the plots quite trivial, really, only take a few seconds. Excuse me. So this is one of the example of one of the animations that we sort of produced, and I'll just let this running for a few cycles. So as you can see here, it's very transient, if you like. On this, we're lucky in the sense that there was no sort of pooling of gases anywhere. Towards the end of the animation, you can probably see, or hopefully see, it's probably running a little bit fast, but if I let it run a few times, you can hopefully see that there is a little bit of pooling in the lowlands. The contour lines here show the heights of the topography. You can see that the sulfur dioxide is tends to pool in the low-lying regions and get deflected by the sort of significant mountains and hills around there. And so this was the kind of plot that was being produced operationally during that early eruption phase. The sort of concentrations of sulfur dioxide here are reported at about 30 meters above ground level. So this is in effect the lowest model level, and these are in micrograms per meter cubed. So the concentrations here would not be high enough to seriously harm anybody. Even if you were quite close to the plume, for non-asthmatic people, you would probably be okay. You would be able to smell it and maybe even taste the sulfur dioxide, but it's unlikely at these concentrations to giving you breathing problems. Especially, as I say, the winds that occurred during this time were quite varied, and you can see the plume moves around quite a lot. But that's a good thing because it stops the plume sort of pooling up too much. And this is just a kind of representation of it, as if you were looking from an elevated point, looking down upon the plume. So this is a nicer surface of gas concentration. So it does spread a long way. And it's, as you can see, it's very, although the sort of envelope of it, if you like, the outline is quite simple. You could, like in those initial examples, you could take a pen and quite easily draw an outline around it. The actual individual sort of structure within it is very, very complicated, caused by the motions in the atmosphere. And you can, this is a satellite image on the 14th of April. This shows the sulfur dioxide as reported by the satellite. So this is as close to observations as we get, really, for this kind of purposes. So that's showing you in the warm colours again where the sulfur dioxide is on the peninsula of the southwest of Iceland, and we can superimpose on that our wharf runs, and it did in this case it did a pretty good job of capturing where the plume goes for that particular time and date. So we're quite happy with that. And of course, with any model like this, the results are really only as good as the meteorology that goes into driving the model. So you can have the fanciest model in the world and the biggest supercomputer, but if the meteorology that goes into the model is wrong, then you will get the wrong result. But I think during we were quite lucky, and we sort of followed the results quite closely. And so this is my last slide, actually, but we did plan to install lots of air quality stations in Iceland in order to test the model, and that was getting well underway. But then towards September of last year, the sort of events started to sort of diminish in intensity, and by October, the Icelandic Met Office declared the incident over. And this is the air quality measurements are online, so you can look at these freely online, and these are from earlier today, and they show across the entire peninsula is green. So when the concentration of sulfur dioxide starts to increase, these sort of balloons start going to orange and then to red. But at the moment they're all green, so there's nothing really much happening there at all. So what we're going to do is we're going to take the historical series of these air quality measurement sites and compare them to the model. And try and figure out some ways to improve the model. We know a number of ways in which it can be improved. But in summary, so we've used ARCHER and ARCHER2 to simulate volcanic plumes, volcanic gases. These results have been shared with collaborators in the Met Office and the Icelandic Met Office, and we're hoping to sort of to verify them against measurements. And with that, I will say thank you for listening, and I'll wrap it up there. Thank you.
Thanks very much for that talk, Ralph. That was great. If there's anyone who would like to ask any questions, you can feel free to either put it in the chat or raise your hand and use your mic.
Shall I stop sharing at this point, or?
I think it's fine to leave it sharing in case you want to show some slides.
Of course, yeah. Good point.
Yeah. Mark Richardson.
Sorry, I can't see the chat. Yeah.
Hello, good afternoon.
Hi.
I'm just curious about the injection point and the size and how your grid will vary around that if you have to have a very small grid cell for the injection point.
Yes, that's a good question. So in the operational runs that we did, which were at a lower resolution, you just have to assume that the injection point is at one grid point. So if you've got, I think we were running at a grid resolution of about 500 meters, which was about the actual sort of initially the size of the sort of crater was about 500 meters across. So we had to assume that there's nothing else you can do really. You have to assume that one grid point equals the source. So that's effectively a point source. But in subsequent simulations, hindcasts, if you like, we've lowered the resolution down to a couple of 100 meters. And if you spend a bit of time and you do it quite cleverly, you can effectively create something that looks like a sort of a lot of craters aligned. The actual craters, the vents were aligned along a southwest northeast line, so we could actually produce like a line of craters, but that required a high resolution. In the low resolution runs running operationally, where you want the results quickly, we just had to assume that the vent or the source was just at a single point. And I don't know if that answers your question.
Thank you very much. That's good.
There's also a question from Helen in the chat. Very interesting talk, thanks. Is it possible to give the volcanic tracers physical properties such as solubility or sedimentation?
I'm not sure about the solubility one. That's a good question. The solubility, really, I mean, you can turn the microphysics on in the model, and so any potential sort of particle could interact with microphysics, but that would probably be a bit beyond the use for which we intended it. But the sort of the particle properties, yes, sedimentation, yes, we have got a version where it does sediment, and there are a number of ways you can do that. I mean, we've done it by adding a sort of fall speed. So the fall speed would be determined by the sort of mean free paths. So what we did was, so at each stage in the model is an advection stage where the tracers would be moved around. So the tracers are moved around by the winds in the model. So just before that stage, you can add a settling velocity so that the actual tracer particles start to fall out, and then you would advect the remaining sort of model points without that sedimentation. Perhaps I've not explained that very well, but yeah, in short, you can do it, yes, by being sort of clever. You can add a sedimentation to it. I've not shown any examples of that here, but it is possible to add the sedimentation based upon and add more than one sedimentation rate as well in order to simulate different ash-sized particles. So yeah, that is possible. We've done that in the past.
All right. There's another question from Andrew, which is, how did your results compare with those issued by London VASC?
Well, the London VASC, as far as I know, because it wasn't a danger to aviation, and was more of a gas simulation exercise in this case. I've not seen any results from the London VAC, so I'm not quite sure about that. We did some simulations with the Met Office. Look, the Met Office in one of our sort of talks or online meetings around about this time, and the Met Office were also doing simulations of sulfur dioxide, and the conclusion was it's a difficult thing to do. It's a very difficult thing to do there, and our results did look promising compared to some of the observations, and that was why we wanted to put some more air quality stations out there in order to get a more comprehensive range of stations to compare with. It's quite a difficult thing to do because if you're comparing with one air quality station, you might be the plume correctly represented but just slightly in the wrong place, and if it's just one air quality station, that would effectively suggest that you've got it wrong when you were in fact very nearly close to the truth. And it's a similar problem to sort of verifying rainfall amounts and so on, whereby you get the sort of the correct result but slightly off centered. Well, that's something that we're working on at the moment to try and verify them against actual observations. Yeah. Thank you.
Andrew, do you want to ask something over the mic?
Yeah, just a quick follow-up. You mentioned in your presentation that so you said that the simulations that you've been doing were not possible or unimaginable without ARCHER2.
Yes.
Why was that? I mean, could you not Jasmine servers or other compute servers? Why was ARCHER2
yeah.
the deal?
Well, I mean, it was, I suppose the answer to that is this could have been installed on Jasmine, and a similar version to this is installed on Jasmine. I guess, well, without sounding like a sort of trying to advertise Archer, it did seem to be very reliable, and we were given this emergency allocation. So we've got exclusive use of 256 processors, and everything was very sort of reliable. I mean, this could be done on Jasmine, yes, but I mean, at the time, everything was compiled and running on Archer, and perhaps that was a wrong choice of words on my part. It's not unimaginable on other competing platforms. It was convenient, and the good folks at Archer had allowed us exclusive access to 256 processors for about a week, I think it was. So yeah, it was a poor choice of words on my part, so apologies for that. But yeah, I think it just sort of fell correctly for us at the right time.
Okay, thanks.
And there's a follow-up question from Helen saying, are there disadvantages to running volcanic plume simulations using WRF, e.g. over dispersion?
Yeah, I mean, there are a number of problems using any model, I guess, and it's trying to do the best that we can with a given model. So I think the dispersion properties that we tested been tested against as many theoretical examples as we can, and we're pretty happy that the dispersion is sort of follows lots of theoretical sort of benchmarks, if you like. So there are a number of integral plume models for volcanic sort of entrainment and so on. And the WRF model in the paper that we sort of described this volcanic model, it does follow a number of sort of theoretical models, and the dense gas model does follow theoretical models of sort of speed of density currents and so on, and we've all compared the sort of dispersion of dense gases compared to cold gases, which behave in similar ways in certain circumstances. So there are a number of tests that you can do, both theoretical and semi-theoretical. But it is again, it is a numerical model, and if, as I sort of stressed at the end point, if the meteorology that goes into it is incorrect, then the whole thing will be incorrect anyway. So there are a number of things, caveats, that you have to bear in mind, but then that applies to any and all dispersion models of this kind. None of them are perfect, and they've all got drawbacks of some kind. It's just trying to do the best you can with the sort of models at your disposal, really.
Andrew, do you want to ask another question?
Yeah, so that sort of brings up the question then, why did you choose, well, you explained why you used the WRF model, and the US data that goes into that model.
Yep.
Is there a reason why you had no access to the Met Office model data?
Yeah, I mean, yeah, there is. I do not have access to the Met Office model data in the forecast sense. So the American national centres release their forecast data publicly available, and you just click on an FTP server and you download it, or have some sort of script to do that for you, and that's essentially why. Yes, because I think that's the reason why a lot of people use WRF, is that the actual stuff that you need to drive the model with, is including forecast data, it's all free. Yes, and
Right.
that's essentially why we used it. Yeah.
Thanks, Ralph. Are there any other questions? Okay, since there don't seem to be any more, I'll just thank Ralph one more time for giving us that talk. And yes, thank you all for coming, and hope you enjoyed this webinar. This session has been recorded, and it will be available on the ARCHER2 website following the talk. Thanks.
Thank you. Thanks a lot.